Okay, children. Now I resume from Newton's second law of motion. Now, according to Newton's second law of motion, what is the statement of Newton's second law of motion? It says that rate of change of momentum of a body is directly proportional to the force applied on it, and it takes place in the direction of the force applied. I repeat, the statement of Newton's second law of motion is rate of change of momentum of a body is directly proportional to the force applied on the body, and it takes place in the direction of the force applied. Okay, so this is Newton's second law of motion. Now let me convert Newton's second law of motion, the statement, into a formula. Now what is rate of change of momentum, children? That is delta P upon delta T, because we know P is momentum, change is delta P, and rate is with respect to time. Okay, now we know that according to this statement, rate of change of momentum, that is delta P upon delta T, is proportional to the force, that is capital F. Okay. Now, what is the rate of change of momentum? Children, if you remember, in the previous lecture, in the previous section of my lecture, I had explained that change in momentum is nothing but it is equal to mass into acceleration. Just now, see, here I have said, na, rate of change of momentum is mass into acceleration. So, what do I do over here? In place of in place of the force, I say rate of change of momentum is also equal to ma. Okay, so what is rate of change of momentum according to Newton's second law? It is directly proportional to force applied. And according to the previous thing which I taught, rate of change of momentum is equal to ma. Now, when I combine these two, what do I get? I get F is proportional to ma, because when this is proportional to F and the same thing is proportional to ma, therefore I say that F is proportional to ma. Now when I remove the proportionality sign, I use a constant of proportionality, and that is denoted by capital K. So it says F is equal to Kma, and the value of K is equivalent to 1. So therefore I reach a formula F is equal to ma. That is, F is equal to mass into acceleration. Right, children? And again, if I pick up the same thing, that is F is proportional to delta P from the statement of Newton's second law. If I pick up this, that F is proportional to delta P upon delta T. Now, it has two conditions, children. You remember, I told you, delta P has two conditions. One is delta mv and the other is m delta v. Now, when I substitute this in this particular formula according to Newton's second law, I can write delta P as delta mv. I can write delta P as m delta v. It's not a derivation, but you should know that under two different conditions. And what are the conditions? Here, the mass remains constant and the velocity of the body is much less than the speed of light. I'm just revising the things which I've already taught, children. Okay. And here, when is change in momentum equal to change in mass and velocity both? When the speed or the velocity of the body is equivalent to the speed of light. Okay, so just remember and recollect all these things. Change in momentum could be change in mass into velocity upon time, or it could be equal to mass remaining constant, change in velocity upon time. And what are the conditions? I have written once again below. Okay, and what is the main formula for Newton's second law? F is equal to ma. And how have I derived this formula? From the statement of Newton's second law, which says that rate of change of momentum is directly proportional to the force applied and takes place in the direction of the force applied. And I already know that rate of change of momentum is ma. So I just combine 1 and 2 and write F is equal to ma as my formula. Okay, so remember, and you should be able to understand this topic very, very carefully. Okay, children? Now, we know that F is equal to ma. Let's focus on this formula. F is equal to ma, which is the formula for which is derived from Newton's second law of motion. Now, looking at this formula, children, I could plot 3 graphs. See, this is the formula F is equal to ma. I have plotted 3 graphs, children. Look at the difference between the 3 graphs. The first graph is between force and acceleration. Between force and acceleration, and they are directly proportional to each other. Therefore, the graph is a straight line, and here the mass remains constant. Okay. Look at the second graph. It is plotted between F, that is force, and mass of the object. It is again a straight line because force is directly proportional to the mass, or the mass is directly proportional to the force, and the acceleration remains constant. Look at the third graph. It is plotted between mass and acceleration, and it is inversely proportional, and F remains constant. Now, what do you mean by, let us look at this one, first one. We have studied that when the force applied is greater, the acceleration of the body will be greater. So, therefore, it is directly proportional. In this case, when I say that the mass of the body is greater, the force required to be applied on the body should be greater. So, again, it is directly proportional. But in the third case, when the mass of the body is greater, the acceleration produced will be less. So, therefore, it is inversely proportional. So, please, these graphs could be asked for plotting, or the graphs could be asked for explaining, or the conditions for these graphs could be asked. Here, what is the condition? Mass remains constant. What is the condition in the second one? Acceleration remains constant. What is the condition in the third one? Force remains constant. And what is the interrelation? Directly proportional, and inversely proportional. Okay, children? Fine. Now we come to force. What is the SI unit of force, children? It is Newton. And what is the CGS unit of force? It is Dyne. Okay. So how do I come to Newton? How do I break up, or how do I, what is 1 Newton equal to? 1, if I use this formula, F is equal to MA, 1 Newton is equal to 1 kg, okay, into 1 meter per second square. Similarly, 1 Dyne is equal to 1 gram into 1 centimeter per second square. Now, if I want to work out an interrelation between the two units, that is the unit of SI unit of force and the CGS unit of force, what do? I pick up this. I say 1 Newton is 1 kg into 1 meter per second square. Now, what is 1 kg equal to, children? It is equal to 1000 grams. Okay. And what is 1 meter per second square equal to? 100 centimeter per second square. And when I combine these two, I get 1 Newton is equal to 10 to power 5, because there are 5 zeros. Gram centimeter per second square. But then what is grams centimeter per second square? It is equal to Dyne. So I substitute here and I get 1 Newton is equal to 10 to the power 5 Dynes. This could be asked for 2 marks. Derive a relation between the SI and the CGS unit of force. SI unit of force, Newton. CGS unit of force, Dyne. And you start with 1 kg equal to 1000 grams, 1 meter is equal to 100 centimeters, combine the two and you get 1 Newton is equal to 10 to power 5 Dynes. Okay, children, this and the last topic for today is, which is quite simple. It says what is the relation between Newton's second law and first law of motion. Now, we have looked at the first law already. We have studied about it, that a body remains at rest or a body remains in uniform motion unless and until a force is applied to it, external force is applied to it. Now, what was Newton's second law? Now, we know Newton's second law is rate of change of momentum is directly proportional to the force applied and takes place in the direction of the force applied. Yes, and I derived, if you remember, I derived the formula F is equal to ma for Newton's second law. Now, if F is equal to ma is taken and I say that the force applied is 0, let us suppose that I say force applied on the body is 0. Now, when the force applied is 0, naturally the body will not move. And if it is not going to move, there will be no change in velocity. And when there will be no change in velocity, the acceleration will also be 0. Right? So this means, what does this mean? That when in the absence of an external force, there is no acceleration, and if there is no acceleration, the body will continue to remain at rest, and if the body is already moving in one direction with uniform speed, it will continue to remain moving in with the same speed unless and until an external force is applied. And that is what is Newton's first law. Got it, children? See, I said when no force is applied here, there is no acceleration. This is the second law. right? And if there is no acceleration, means there is no velocity. And when I say there's no velocity, it means the body will continue to remain in rest or in uniform motion unless and until external force is applied. And that is Newton's first law. So this is how Newton's first law and second law are related to each other. So remember, these laws are interrelated. And in the next class, children, I am going to focus on the day-to-day activity examples of Newton's second law of motion. So I want you to revise thoroughly what I have taught in today's class, so that in the next class when we meet, we will discuss the different examples from our day-to-day life which are related to Newton's second law of motion. Thank you, children.